Search and rescue crews continue to look for survivors in the US state of Kentucky, where record flooding has wiped out entire communities. At least 28 people have died, although the state's governor warned the number could rise.
A mountain moves. It all began with a single picture from space. A satellite that usually watches weather and land sent back a map. On that map, one small area in the Appalachian Mountains looked different. The ground there had lifted up. At first it seemed tiny, just a few millimeters. Satellites can be noisy, and small jumps can be errors. But the same place rose again the next day. Then other satellites said the same thing. Ground sensors also showed the rise. That made it real. When scientists compared older maps, they realized the change did not stop. Over weeks, that small motion became a dome. In a few places, the ground rose several centimeters. A few centimeters might seem small, but across many square miles it mattered. It meant something strong was pushing from below. People who study mountains call the Appalachians retired giants. They formed hundreds of millions of years ago when continents slammed together. Over time, wind, rain, ice, and rivers wore them down until they became soft, round hills. These are not the young, sharp volcanoes of the West. They are older and usually calm. So when the satellite image showed motion, it surprised experts everywhere. The US Geological Survey, the USGS, checked the data fast. They ran tests, compared instruments, and asked other agencies to look too. The evidence kept pointing the same way. The ground was lifting. Within days, the USGS issued a red alert. That is a high-level warning. It tells local leaders and the public, pay attention, prepare, watch for more information. The words red alert reached small towns, school boards, and state emergency teams. People felt a quiet shock. The place they thought was steady was now moving. Teams from universities and agencies formed a task force. They flew in instruments and trucks. They began to listen and watch closely. Scientists had two urgent questions. What is pushing the ground up, and how likely is it to cause damage? Both questions needed fast answers. The mountain had given a sign. Now humans had to find what came next. Part 2, the Appalachian Mystery. The Appalachian chain runs a very long way, from the far south in Alabama and Georgia, through Tennessee, North Carolina, Virginia, West Virginia, and up toward New York and beyond. It is a wide, weathered backbone of green hills, clear streams, and old rock. Towns nestle in valleys. People farm and hike there. Families have lived in these places for generations. Long ago, these mountains were once as high as waves of stone. They came from giant collisions of land masses. Over the eons, layers folded and broke and then eroded down. Rivers carved deep gaps. Glaciers scraped and smoothed. Now the land is softer. The peaks are rounded like old tree stumps. That long history gave people confidence. Engineers built bridges and roads. People planted towns where they felt safe. The bedrock underfoot had been quiet for a long time. So why did the satellite show a dome of uplift almost the size of a small city? The area covered nearly 50 kilometers in some maps. In places, the ground rose more than 6 centimeters in a short time. That dome shape was odd. It looked like air slowly pushing up a blanket. Scientists compared the shape with more than a dozen types of ground movement and could not find a perfect match. They dug into old maps and records. Mine maps showed old shafts and tunnels in some areas. Geological surveys, some done long ago, had showed buried faults and layers of different rocks. None were a smoking gun. The new movement did not line up neatly with any single past feature. Local people told stories. Farmers described wells that had always flowed a little the same way. Hikers said springs had changed their taste. Old letters in town libraries mentioned small shakes decades ago. Those notes became clues. When scientists combined modern instruments with these old stories, a pattern slowly grew. Tiny hints of change had been there for years, but now something had sped up. This event asked a big question. Can old, quiet mountains suddenly act in ways we expect only from young, active ranges? The Appalachians carried deep memories of Earth's ancient drama. Now they were adding a new scene, one scientists had not expected in their textbooks. Part 3, First Clues, Signals in the Data. When the satellite flagged the uplift, teams pulled together every data set they could. They pulled up GPS logs, long-term leveling surveys, borehole temperatures, and even old farm records. They examined each line of data for small trends. At first, the clues were whisper quiet. ground movement of millimeters recorded over years. When stacked together, those tiny shifts formed a slow rise. Then the slow rise sped up. GPS stations in the region, the same instruments used to make maps and guide highways, began to show steady upward motion in the same ring the satellite saw. These instruments are precise enough to measure the growth of your fingernail every day. That precision made the slow acceleration impossible to ignore. Seismometers told another part of the story. The instruments registered many small events, but not the sharp, immediate quakes that break rocks. Instead, they logged long, low tremors that lasted longer and had a deep tone. Scientists call these deep long-period events, or DLPs. DLPs are often linked to the movement of fluids or partially molten material deep in the crust or upper mantle. They can appear when magma or hot fluids try to move through the rock. Why would DLPs appear under an old mountain range? One possibility was that a fluid or hot rock pocket was shifting. Another idea was that pressure on a buried fault pushed water and gas into new cracks, creating slow vibrations. DLPs say something is moving deep down, but they do not alone name the mover. Other instruments added hints. Gravity surveys showed tiny changes that could mean mass was shifting under the dome. Magnetometers picked up small pulses in the magnetic field, an odd signal that can come when fluids carrying charged particles move. Borehole thermometers in deep wells recorded slight warming. Groundwater chemistry tests detected tiny rises in dissolved carbon dioxide and sulfur-bearing compounds. None of these hints screamed a single cause. Instead, they formed a chorus. Heat, fluids, pressure, and motion were all linked. The pattern suggested that something deep in the crust was changing in multiple ways. It had been quiet for a long time, and now it was active. That active chorus convinced the USGS to keep the red alert. The sensors told real stories. They did not promise a disaster, but they did promise that the Earth was moving differently than before. And that was enough to ask people to be ready and scientists to learn fast. Part 4. Theories emerge. When odd things happen in geology, scientists make careful lists of ideas. They test each idea. They look for evidence that fits the idea and for pieces that do not. For the Appalachian uplift, teams of geologists, hydrologists, geophysicists, and engineers met daily to debate and test theories. Magma intrusion, a rise of magma, molten rock, can lift the ground as it collects in a chamber. In active volcanic areas, magma domes create maps that look much like what satellites saw. If magma were slowly moving under the Appalachian crust, it could explain the dome shape and some of the DLPs. But the Appalachians do not have shallow magma systems known today. If magma were present, it might be deep and small. Scientists looked for signs of heat or volcanic gases. So far, heat signals were small and gas readings were low. That did not rule magma out, but it made the explanation less simple. Theory: fluids and pressure. Sometimes hot or pressurized fluids trapped under layers of rock move. These fluids can be water-rich and dissolved gases or brines carrying minerals and carbon dioxide. When pressured, fluids can push on the rock above. They can also cause DLP-like tremors as they flow in cracks. The small rises in dissolved gases and the borehole warming fit with fluid movement. If an ancient, deep aquifer was being squeezed, it could create uplift without magma. Models showed that a large fluid pocket could make a dome like the one seen. That made this theory strong. Theory: reactivated faults and rock deformation. Buried faults can slip after long sleep if stresses change. If a fault edge moved in one place and was held in others, the ground could bulge without a clear break. Fault motion could also force fluids out of the rock that had been trapped for a long time. Some old mine maps and seismic reflection studies pointed to deep buried structures that might be reactivated. Fault motion alone might not explain all signals, but a slipping fault coupled with fluid migration could. Theory: a new mixed process. The most cautious explanation was a mix. The crust under the dome might be responding to several forces at once: a slow injection of fluids, warming of deep rock, and tiny slips on a buried fault. The system could be complex and non-linear. That means small changes could suddenly lead to larger motions in unexpected ways. Scientists ran computer models for each theory. The models used physics equations for heat, fluid flow, rock strength, and fracture behavior. Some models mimicked the dome growth and DLP pattern, but none matched every piece of data perfectly. That left experts both uneasy and curious. The lack of a perfect fit meant the system might be unlike common textbook examples. It also meant more data and more time were needed. In public briefings, scientists stressed that theory testing is normal. They explained why each idea was possible and why each had limits. The aim was not to cause fear, but to show the facts and what could follow. The next steps were more monitoring, more field sampling, and more tests that could narrow down the true cause. Part 5. Communities react. When authorities issued the red alert, life changed in many small but important ways. Local officials did not order people to leave. Instead, they urged readiness. They wanted to avoid panic and keep the public safe. Emergency managers activated plans. Shelters were checked and stocked. Communication lines were opened with county leaders and school districts. Officials set up call centers to answer questions. They also hosted town halls where scientists explained, in simple terms, what the data meant and what residents could do. Homeowners packed go bags. These bags had water, non-perishable food, flashlights, a radio, a first aid kit, and copies of important papers. Families planned meeting spots in case phone networks failed. Some neighbors made buddy systems to help elders and people with disabilities. Schools used the alert as a voice teaching moment. Teachers held classes on how Earth moves. Students drew maps of safe routes. Kids practiced walking drills to school meeting spots. The drills were calm and matter-of-fact. They helped the children feel less scared and more ready. Local businesses also prepared. Grocery stores kept extra bottled water on shelves. Gas stations checked pumps. Utility crews inspected broken power poles and leaky gas lines near the uplift zone. Road crews prepared to respond to landslides and fallen trees. Hospitals checked emergency plans for extra patients, just in case. Social media had mixed effects. Helpful information spread fast. Maps, official links, and safety tips. But rumors and bad information also traveled. County officials worked hard to post verified updates and to correct false claims. Journalists were given access to the scientists and asked to report carefully. Community volunteers played a big role. Churches, schools, and local nonprofits coordinated food drives for shelters. Neighbors checked on elders. People who owned heavy equipment offered it in case roads needed clearing. The kindness in many towns became a strong force for comfort. Through all this, officials repeated the same guidance. Prepare, but don't panic. Keep official phones and web pages open. Follow local leaders. If evacuations become necessary, they will be ordered clearly and early. Until then, readiness and community care were the best steps. Part 6. Eyes in the sky. Satellites remained vital for tracking the dome. Different sensors gave different views. Radar satellites using InSAR gave maps of ground deformation by measuring tiny changes in distance to the ground. Those maps showed the dome clearly. Optical satellites gave sharp photos of the surface and helped place field teams. Thermal satellites looked for heat. So far, thermal signatures were weak. Space agencies pooled data. Partners from allied countries shared radar images, and scientists combined them to make more accurate maps. The satellite picture showed not just uplift, but how it grew and shifted over time. Sometimes the dome grew more quickly on one side. That hinted at underground channels where fluids or weak rock might guide the motion. Space-based gravity missions also helped. They measured tiny changes in gravity that can indicate mass movement underground. These measurements suggested something might be redistributing deep in the crust. The gravity signals were subtle but consistent with a moving pocket of mass, possibly fluids or a change in rock density. Satellites also helped emergency planners. By tracking where the uplift was worst, they helped identify roads and infrastructure that might be at higher risk. This allowed crews to pre-stage equipment near likely trouble spots and to plan detours for critical deliveries. The satellites did not answer the why fully, but they were the best long-range monitors. Combined with ground instruments, they formed a system that watched the dome in both detail and breadth. The eyes in the sky kept sending back data day after day, making sure the scientists had the clearest possible picture. Part 7. Strange anomalies. Beyond uplift and DLPs, other odd signals kept appearing. magnetometers registered small magnetic pulses when seismic energy spiked. These pulses can come from electric currents generated by moving fluids or changing mineral magnetism when rocks heat slightly. The pattern of magnetic pulses matched some of the DLP timing. That suggested a linked process producing both seismic and electromagnetic effects. Groundwater wells gave another surprise. In some wells, small increases in dissolved carbon dioxide and sulfur compounds appeared. These gases can originate from deep rock or from organic decay. The pattern and location of the gas upticks made deeper sources more likely. In several springs, water temperatures rose by fractions of a degree, small but measurable. Even plants and animals showed reactions. Farmers reported cows grazing in new areas. Dogs barked more at night in certain valleys. Bird migration patterns seemed slightly shifted. Scientists know that animals sometimes sense changes humans do not. They can detect low-frequency vibrations and tiny changes in water and ground chemistry. These reports were collected carefully, cataloged, and compared to sensor data. Another curious sign came from old mines. In several abandoned shaft areas, gas sensors recorded higher readings than normal. Mines can act as vents for deep gases when pressure patterns change. That raised concerns for mine stability and air quality in old shafts, and teams moved quickly to assess risks for hikers and curiosity seekers who sometimes explore old mine entrances. Together, these anomalies built a more detailed story. Heat, fluids, minor magnetic effects, and animal behavior were all part of the same system. Each thread did not alone prove a single cause, but altogether, they suggested an active subsurface process involving both mechanical and chemical changes. Part 8. Global attention. The unusual event drew attention from around the world. Scientists from countries with experience in volcanic and crustal unrest traveled to help. Those experts had seen domes before under volcanoes and shared lessons learned. Engineers experienced in landslide and infrastructure protection lent advice on protecting critical corridors and bridges. International research agencies offered funded instruments and analysis tools. Space agencies shared more satellite passes. Universities shared modeling code. The global science community worked together in a way that usually happens only after major events. That cooperation sped up understanding and gave local officials trusted voices from many places. News cameras and reporters also arrived. Some stories were careful and accurate, others were sensational. Local officials tried to balance transparency with calm. They held press briefings and asked journalists to use verified data. Scientists gave interviews, but also emphasized uncertainty. They had strong clues, but not a final answer. On the academic side, workshops formed. Scientists wrote quick review papers to summarize the data and explain models. These papers helped other experts weigh in and test ideas. The event became not only an emergency story, but also a scientific case study that might change how people think about mature mountain ranges. Despite the global interest, locals kept life moving. Farmers harvested crops, schools kept classes, hikers still enjoyed trails outside risk zones. The added help and scrutiny, however, meant better data and more resources to keep people safe. Part 9. The unknown future. Time stretched forward with both hope and caution. Some weeks the dome showed signs of calming. The uplift rate slowed and DLPs dropped. Other weeks, the dome pulsed again, faster. That up and down pattern was unnerving. It showed the system could change direction at any time. Scientists ran many scenarios. Some models showed that pressure could slowly dissipate if fluids found a new path out. In that case, the dome would slowly subside, and the system would calm over months to years. Other models warned that sudden changes in pressure or a cascading failure of buried faults could create rapid ground collapse or landslides. Engineers focused on what could be done now. They inspected bridges, roads, and pipelines that crossed the dome. Where faults or uplift crept under roads, engineers reinforced slopes and secured culverts to reduce the risk of washouts. Emergency managers marked more evacuation routes. Hospitals reviewed mass casualty plans, and utility companies prepared to isolate damaged segments of gas lines or electrical grids quickly. One unknown question was whether the event could trigger secondary hazards. Heavy rain during a period of uplift could weaken slopes and cause fast landslides. Cold snaps that freeze and thaw water in cracks might expand damage. Officials planned for combined events because Earth rarely delivers single problems in neat isolation. The science community also saw the event as a rare study. Long-term monitoring would help answer questions about crustal behavior. Data from this episode could improve early warning systems elsewhere. Experts hoped this would be a moment of learning that would help many communities in the future. For residents, the unknown future was a test of patience. People adjusted their plans and watched official channels for updates. The red alert remained as a guidepost. Keep prepared and stay informed. That steady posture helped communities face each new week with calm readiness. Part 10. The final warning. After many weeks of observation, scientists and officials met to set a path forward. They agreed on 3 things: continue robust monitoring, maintain public preparedness, and expand research to narrow the cause. The USGS kept the red alert in place as a precaution. The message was simple: we do not know all the answers, but we have clear signs that an active process is underway. The alert asked people to be ready and to follow guidance from local authorities. Officials recommended specific steps. They urged people in the uplift zone to prepare go bags, check emergency plans, and secure valuables. Local governments trimmed trees that could fall on roads, inspected dams and levees, and prepared shelters with food and power. Utilities planned rapid response teams to isolate and repair damaged lines. Scientists committed to transparency. They promised regular public briefings and clear, simple summaries of what the instruments showed. They explained their best and worst-case scenarios and why they favored caution. They also emphasized the chance to learn. With the data streaming in, they could test new models and better understand how ancient crust can wake in modern times. The final warning was not doom. It was a call to respect the evidence and to be ready. It was an invitation to learn from a living Earth. For many, it was a reminder that our planet is dynamic and that science and community together offer the best defense. The Appalachian Uplift is a story of surprise and of teamwork. It shows how modern tools, satellites, GPS, seismometers, and chemistry tests can catch small changes and turn them into knowledge. It shows how communities, scientists, and officials can act together when the ground beneath our feet changes. If you care about this story, please do 3 simple things. 1. Stay informed from official sources. Follow the USGS and your county emergency management for verified updates. 2. Be prepared. Make a basic emergency kit: water, food for 3 days, flashlight, batteries, a radio, medicine, and copies of important papers. Talk to neighbors and make a plan for people who may need help. 3. Share responsibly. Help friends and family by sharing accurate information and official links. Avoid spreading rumors. If you want to follow this story as it unfolds, subscribe to this channel for regular updates. Hit the bell so you get an alert the moment we post new findings. We will share clear summaries, practical safety tips, and expert explanations that cut through fear and focus on facts. Earth can surprise us, but when science watches, people prepare, and communities help each other, we all become stronger. Thank you for watching. Stay calm, stay ready, and stay curious.